So welcome here, everybody. Today we have Ariel Ekgren from ri.se, our colleague, who will talk about CLIP and diving deep into it. So I will leave the floor to you, Ariel. The meeting is being recorded, and you can tell people how you like to take questions. I can forward questions from the chat, for example. Right?
Yeah. So my name is Ariel Ekgren, and I'm working in the Natural Language Understanding Group at ri.se. And I'm going to start this. It's going to be quite an informal talk. I'll try to go through CLIP, and we'll end with a live demo. So in my opinion, you can almost interrupt me if you want, if you have questions, but you can also write them in Slack. So I'm going to talk about CLIP from OpenAI, which is a new way of connecting images and text. And in a sense, they were not the first ones to do this algorithm that I will explain with these tools, but they were the first one to do it on scale and really showing the power of this. So I will start by talking a bit about the model architecture and data and training and image classification, and then I will go on to the most fun part, which is image generation. And I want to spend a bit of time on image generation and discussion with you, so I might go quite quickly through these first parts. We'll see. So this is a little teaser for what's to come. So what is CLIP? It's a general image classification model. It's a vision model and a language model, and it's trained on a very large data set. And with regards to being a general image classification model, you can basically create any labels that you want, and this by natural language. And I'll explain how you can do that. But I'll start with talking about the architecture. And CLIP is a transformer model that was first introduced in 2017 and for text. And it made a really big impact on the text world. But since then, we have discovered that transformers are good for almost anything. In CLIP, they use a lot of models, but the best performing models for images and for language are both transformers. And for text, you tokenize text with something called byte pair encoding. And that is what has been used for transformers since the beginning. But it turns out you can actually apply transformers to images, and then you just cut up the image in patches. And you create a grid of image patches, and you have a linear transformation on them. And then you just say, okay, but this is tokens, just like for language. And that apparently works. And if you compare that with convolutions, you kind of, when you look at an image, you look at overlapping patches. And so it's not super intuitive for me that you can just cut up an image and without an overlap and make sense of it. But that's what transformers do. And the transformer architecture consists of a self-attention. So this is a very simplified and brief overview. But in my opinion, transformer architecture consists of two main things: a self-attention layer and a feed-forward layer. And self-attention basically takes the tokens or the input pieces and combines them. So you have an embedding, a word or an image patch, and then from that you create a query and a key and a value, like from one piece, and then you use queries from one patch to match it with keys from other words or patches to get a kind of scoring. And then in the end, it's just a weighted sum of all the input. And the feed-forward layer of a transformer is a classical multi-layer perceptron. And these two parts are combined together. So you have alternative interleaved at self-attention and feed-forward and self-attention, basically. And that is a kind of, in a sense, simple architecture. But of course, there's a lot of details involved with training them and getting a really good performance and making them resource efficient and whatnot. There's a lot of good resources out there. But so clip is two transformers, all right? And then you do some magic with them. And one big piece of the magic with clip is that you have 400 million images that it's trained on, and you have 400 million matching text pieces. So you have an insane amount of texts and images that you gather for this machine learning model. Oh, this is something new. Sorry. Let me just see here. Okay. One second. This is the magic that we're missing here. Let me reload it. So here we have it. So we have a really big data set for the two transformers. And then we use these images and texts and do contrastive learning. So you put in texts in one transformer and you put in images in the other. And then you want to match one text with one image. And you say that Pepper, the Aussie pup, and this image, they should be similar. And you have basically a dot product. And then you say every other image in this batch should be dissimilar. And this is not new either, but the way they do it with the clip is, again, on a very large scale, because they use a mini batch size of 32,000 examples, which is insanely large. And then, of course, so with contrastive learning, you want to have many examples because that helps the model to learn what is not interesting. But in order to reach this, imagine trying to fit 32,000 images on a single GPU. That's very hard without a lot of hacks. So they use mixed precision and gradient checkpointing and a lot of engineering stuff to be able to get this really large batch size. And why am I talking about this? Okay, so it's because you can do really, really interesting image classification stuff. I subtitled it, it can do it all. Right? So how can you now use this framework to do image classification? So basically, you can give labels in the form of text. So here they have a suggestion in the image here, where you have a kind of prompt with the text, a photo of object, and then you can insert objects such as plane, car, dog, and bird. And then you encode like a photo of a plane, a photo of a car, a photo of a dog as texts. And then when you input this image of a dog, you just compare it to each of these texts and see where it gets the highest score.
I have a question there.
Yeah, sure.
Is it literally the highest score we're looking for? How is the comparison made? And what if none of the images in this batch fits a photo of a dog, for example?
So it's literally the dot product. I mean, you can of course do a softmax in the end if you want a distribution, but what the transformer outputs is a feature vector, and then they L2 normalize it, and then they take the dot products between these. So it's a normalized dot product, and then they just look for the highest score. And with regards to your second question, it's a very fuzzy clip, right? So it's gonna give some scores to almost anything. But I imagine that you can, if you actually want to use this in production or in practice, I imagine that you can be clever with the texts that you have. So I actually, that's a bit sad. I omitted a fun thing from this presentation.
Can I have a fast follow-up question on
that?
It was
yeah.
an interesting discussion, because I wonder, have they analyzed in the paper, or have anyone done that, the distribution over the dot products? Like, will we have one dominating representation and the others are almost zero, or will they be more uniform? Or is that completely dependent on the input?
I think it's completely dependent on the input.
Yeah.
And they go quite a bit into detail on something they call prompt engineering, which apparently is the future for machine learning, right? So with if you have heard about GPT-3, this really large language model, you can get it to perform very advanced tasks such as translating from English or creating code and whatnot. But you have to write the correct prompt to it.
Exactly. So it would be interesting to see, for example, an analysis on like prompt sensitivity or something like that.
Oh yeah, they have some examples in the paper, and the one I omitted that is really funny is that Clip. It turns out that Clip, this model, can not only interpret images, it can also read. So if you have a picture of an apple with a little note on it, where on the note it says iPod. You can adversarially fool the network that the apple is an iPod. But then you can actually also, it turns out, prompt engineer your way out of it if you write something along Apple without text or Apple disregarding the text. So it's really a strange world. But I'm happy for discussions, but I'll just continue. So they test 27 datasets in the paper of different image tasks, and they receive competitive results on almost all of them compared to a ResNet 50 baseline that they train from scratch on each task, which is quite impressive because these tasks cover a very broad range of subjects or image subjects. But I think there are a lot of limitations, of course, to this. And I mean, this is just from their blog post. But if you just play around with Clip, I would say that this is, in my opinion, it's a kind of a paradigm shift in what you can do. It turns out that, I mean, it's really good for if you have a website with images, or if you have like Kungliga biblioteket, an uncurated data set of images, you can just curate, map all your images to these clip vectors, and then you can filter your data set on this natural language prompts. So you can have black and white images or whatever you can come up with, in addition to actually using it for classification. So I urge anyone that is listening and considering working with vision to at least try Clip out. And me and Fredrik Karlsson, mainly Fredrik Karlsson, I would say, have also done a multilingual Clip where we have done a mapping from multilingual language models and the Swedish language model. so that you can prompt clip in other languages, including Swedish. So if you're interested in using clip, you can check out github.com Fredde Fralland multilingual clip and apply it to other.
Could you say a few words on how this transforms?
So actually, that is not my work. It's Fredrik who has done it, but basically it's a kind of distillation process where we try to. So I mean, in the end, you input some text and you get out a normalized 512 dimensional vector. So what we want to do is to input the translated text and get the output to match this vector. And so this is my favorite thing about. Also, I'm very fast apparently, so this is good. So this is my favorite thing about clip, besides it being a really good general image classification. So wouldn't it be great if we could just write a text and encode it and get an image out from any textual input? And if you are following OpenAI, they released a blog post and a paper about the really large transformer network that they called DALL-E, where they do exactly this. So they generate images from text. And if you do this, if you want to, I mean, clip is two transformers, right? So there is no generative model here. So you can't just get an image out of the transformer. But what if you could back propagate from a prompt into a noisy image or a random image and then update it with the gradient? And to the rescue, we have deep dreaming that was invented a couple of years ago, and a lot of work by a guy at Google named, or maybe he's at OpenAI now, actually. He used to work at Google. Chris Olah has done a lot of work on feature visualization. So if you naively just input an image into a network, say an old image classification network, and you want to maximize you want to update the image for the class dog by applying the error gradient. That's not very useful because you're kind of finding adversarial images most often if you just do it naively. So you will change one pixel and increase the intensity of one single pixel up in the corner. That's for some reason correlates very strongly with dogs. But this, I think, feature visualization movement started a bit by deep dreaming. And what you can do is that you can have a text describing an image. You can encode it. In the case of clip, you can get a loss, and you can input an image, and you can do some magic operations before you feed the image to the clip image encoder. And these magic operations are kind of regularization. So like I said, if you just take the error gradient, so I mean, if I input here a text of a painted portrait of Jan LeCun, could be my text in this example. And then I input a random image and I get the loss. Then if I regularize the gradient, I can get away from this adversarial case where you just like change one pixel or a few pixels. So if you start with the base case where you have a tensor with noise, right? So you don't have anything. You just input a random image into the network. The operations that you can do to get a interesting gradient out from the image encoder with respect to a textual prompt is cut it up into a lot of small pieces that overlaps, and then feed each piece into the image encoder. So you have to, the image encoder is for the visual transformer that is now available from Clip is 224 times 224 pixels. So if you have a large image, you cut up a little piece of the image, you resize it and feed it into the image encoder and say this specific patch should should match the prompt that I put in. And then you get a lot of gradients, but again, it's not good enough. So you have to work a bit with the gradients. And from what I have tried, you can just apply design operation. So you don't want small or large gradients. You want all gradients to be -1, 0, or 1. And that kind of, again, works against this adversarial noise. But now we're in the realm of speculative things. So everything that I have said so far about Clip is by OpenAI. And now we're talking about image generation, which is more of an engineering work at this point.
Perhaps we can add that you're talking about doing backprop through a model and not to do it to update the parameters that you usually do, but you do the backprop all the way to the input where you find it to compute a gradient with regards to the inputs. So then you can move in the input space and you can optimize that and you can find this image that you're talking about.
Yeah, exactly. So again, if anything is unclear or you get any fantasies or anything, just talk out loud. So this image, by the way, is generated by Clip on the text painting of Jan Lekun. So you do these operations on the image, and you can start updating the image to get a pretty picture. So when I first started experimenting with this, I started with the base case, which is kind of just using an image. And I put in the prompts, scientist looking at computer, which is now my new avatar on Twitter, and the neural network and circuit board, and you get this kind of interesting stuff. But then there is also a big open source movement on Twitter with people experimenting with this. So they started using other networks. But okay, here I have another example first we can show. So now we're in the realm of generating things from text. So here is a video I've made where you interpolate between two prompts. So the first, it's starting with the prompt optical illusion, and it creates an image. And then it moves towards the prompt beautiful sunny garden. And it keeps updating the image and zooming into the image while doing this. And you can get some pretty psychedelic things here. So this is, we don't need to watch the whole video, but I think it's a very strange world we're entering here. I don't know. Let's see if we can move.
I have a question, if it's
yes.
Okay. I think this is really, really cool, awesome and interesting. So my first question is, why does this work? Do you have any intuition why it works, or is it just that you've tried random engineering things and it just works? Or is there any mathematical explanation or intuition why you could do this? And that image you get of Lekun in this example, is there any image of him that is similar to this dreaming image? In the data set it's trained on, that is.
Yeah. So with regards to the first question, so I would almost turn it around and say, like, my intuition is that you should be able to backpropagate into an image from an image network. But that's weird. It doesn't work. That's like my intuition. And I think
fair point.
That's because of like these adversarial kind of, so the networks, they really try to find the like optimal configuration of the parameters with like the least resistance. So if it can cheat and kind of look at only one pixel, it will do so, right? So when you backpropagate like naively, you will go towards these like these very weird things that the network look for. But what I do and what you can do is some kind of regularization. Exactly why and how that works, I'm not. That's the area of research. What kind of regularizations are the best for coming close to the input data? And so this image of Jan LeCun is probably not at all present in the data set, but there is a caveat to this image that I'm coming to now. So this like psychedelic video that I showed you, it's only doing deep dreaming on a tensor, and in a sense it's only extracting images from Clip's original dataset that the Clip network has seen. But what if you could use an additional generative network to get a kind of image prior? So, for example, StyleGAN. So StyleGAN is really, really good at making human faces. So what if you could take a StyleGAN image and kind of update that with the Clip prompt? It turns out you can do like the exact same thing that you do with a single image, but you can have a network before that. So here is a portrait painting of Joshua Benju that I had made with StyleGAN and Clip. So here I tell Clip to make a portrait painting of Joshua Benju, and I mean, it's an infinite amount of Joshua paintings that you can see. So it kind of combines the prior from the StyleGAN network with the prior from Clip. And it turns out that you can use a lot of different networks together with Clip. So here we have the video I showed you of Joshua Benju is StyleGAN. So then you can get really pretty and weird or strange faces, right? Because that is the prior from StyleGAN. And then there have come two really powerful autoencoders from one from OpenAI and Dalle, and they have released the code online, and one from another research group that I can't remember which. I think they might be from Berkeley, but I'm not sure. A paper that is called Taming Transformers, where they also have made an autoencoder. These autoencoders take an image and compress it down to one-hot vectors, a couple of one-hot vectors, and then you can, from this very small latent representation, you can get the image out again in high fidelity. But what these two networks have is a really good, like, natural image prior. So if you combine them with Clip, you can get even more kind of realistic, and they add some constraints to the generative process. So here are some examples of things I made. The first one up here is with StyleGAN. It's a portrait of an android in the style of Blade Runner. Here is with the Dalle encoder. It's like an alien playing at the Star Wars bar. And this is not like super semantically coherent, but you have some kind of Wookiee and the feeling of a Star Wars bar, I think. And here is an example from the Dali paper: an armchair in the shape of an avocado, an armchair imitating an avocado. So I'm trying to get it to generate a chair with that is somehow inspired by an avocado, and I think it kind of works. So this is like, to me, this is quite fun, because you start to get to take all these pre-trained models and just like combine them like Lego bricks. And yeah.
Did you say how you connect the generative model to the clip model?
Not exactly. So basically, you create an image from the generative model, and then you feed it through these operations where you cut it up into pieces, and depending on the model, maybe you do not want to sign the gradient, for example. So you have to apply different regularizations, I would say, depending on the model.
But in essence, you keep back propagating through the whole generative model then? Yeah,
exactly. In essence, so you generate a picture from the model, and then you do some kind of this cutting it up into pieces and maybe applying some regularization to the gradient, and then you input it into the clip framework, and you back propagate through the whole model to the so in both the StyleGAN and the autoencoders, you have a latent representation that is the image. So you can freeze the generative network and just update this latent representation. But I think you get a little bit prettier results if you actually dare to update the parameters of the generative network. But then it's kind of overtraining to this one image, right? So you have to load it and train it again for each separate image that you want to.
So in these examples, the generative model is then sort of, it's changing during your predictions because you update the parameters.
Yeah, because that is true. But this is not science at this point. So if anyone wants to dive even deeper into this and write a paper on the optimal way of producing these pictures, I'm happy to collaborate or read it. So I was thinking that we could do a live demo, and I happily ask the audience for prompts. So we could start with the faces.
Have you considered putting this up, or is it up? If anyone could use this after this seminar freely at home?
I am working on a GitHub repository, and there are other resources out there, so I'm not the only one doing this, and I'll call the repository Structured Dreaming. But I'm also trying to write a paper, so I'm not sure if I should publish the code before the paper.
Gotcha.
Or not.
Let us know when it's up, at least.
Yeah. So if you want to generate a human with some features, you can have an alien or whatever. Do you have any prompts that you'd like to try? It goes really fast, so we can try a couple of different ones. Or should I just start with this one? We'll start while you think of prompts. So we start from this person does not exist, and now we're walking towards a painting of an android with a blurred view in the background in the style of Blade Runner. And I mean, now I think I'm a bit used to this, but I've been a bit obsessed by just exploring the universe of weird pictures that you can generate for quite some time here. So there's
now a suggestion from Femi in the chat: an online meeting of researchers in computer science.
So but this is we're coming to the general images. So let's start with our. I can try that. Let's just try it. But we'll have the opportunity to generate any image here. Let's see. It's almost you, Femi. I have no idea what to expect here. Maybe nerdy people. I don't know.
Yeah, apparently yes. That's what we get. So my picture is next, probably.
But I mean, you can quite convincingly generate famous people that Clip has seen. So he has seen 400 million pictures, which I think has a really good a broad cover.
So will there be? Can you make an analysis of the kind of bias that you have in this model? What is a computer scientist, for example?
Yeah.
Is a computer scientist from Sweden or from India?
Clearly,
yeah. Yeah, I think there's a lot of bias, female, male, whatever, present in this data.
I don't know if you were there yesterday, Ariel. We had this NLP webinar about gender bias in artificial intelligence.
Yeah.
It would have been really relevant to try out a few images.
Yeah. Portrait painting of a cultist, right? So this is, we can move on to the other model. But I mean, you can really get some weird stuff going here.
How are two images related in this, in between iterations?
So basically, since this is the StyleGAN model, and it has a latent space. So I'm sampling like arbitrary pictures from this latent space and says that any, and if you walk around in the StyleGAN latent space, it can be old people, young people, men and women. So I'm just sampling.
But are you sampling one latent vector and then moving around from that one, or is it different latent vectors in every iteration here?
So in this case, it's different latent vectors, and I update the whole model and not the latent vectors. So I'm asking the model to only produce people that fits the prompt in a sense. But this is, there are a lot of examples online of people just moving the latent vector to find the StyleGAN model that is most close to the prompt.
How much of a bias do you introduce by, because you start with an image from this people don't exist.
Yeah, exactly.
And it seems like you stay on sort of a portrait here.
Yes.
The meeting of computer scientists, there was only one person there.
Exactly. So let's move on to the taming sorry.
There are a couple of suggestions in the chat, but you'll have to decide when to.
Well, I mean, so what we have a little bit of time, so we can probably try them out. So now we have moved on to this taming transformer general image thing. So here we can try something from the chat, which is.
So Mishat is the next physicist, and then a portrait picture of God.
Yeah. So try a physicist. Okay, but let's just try physicist here.
It's from the other side of the building.
So now we're in the domain of general images here. So
I get the picture. Thank you.
So here we have to have a bit of patience, I think. So maybe this is not as...
So what was the starting point now as compared to StyleGAN?
So now the starting point is a random latent vector for this taming transformer autoencoder.
Okay.
And basically the taming transformer autoencoder can, with quite good results, reproduce almost any picture. I mean, it's not perfect.
It seems like we have a physics lab here.
Yeah.
Would it help if you said a portrait of a physicist?
So now we're not in, I mean, we can try, but I'm quite sure we will get really ugly people because clip let's try here, portrait of a. So since clip is not a generative network, it's okay if the image contains dogs everywhere, in a sense, if you understand what I'm saying. So it will not discriminate a weird picture with dogs in the sky necessarily.
You just made a physicist Picasso.
We are definitely seeing glasses emerge here.
Yes.
Yeah. And the more elaborate the prompts, the more weird, fun things you can get out. I think. So
this is like dreaming of Einstein.
And we see a tendency towards male pattern baldness as well. So that's a significant feature.
Let's try. We can do a portrait picture of God with the StyleGAN. So I'll try the answer to everything here. To the while it's training. And everything, but I think it's really, when you start to explore this, it's obvious that there are some, so you can actually produce really high fidelity pictures that's sometimes of that it looks almost real, and then you have some very weird like interpolations as well. So I think what clip has good representations that fits human intuitions in some parts of space, like you don't want a car upside down or whatever. But in some places, it interpolates in latent space, and it really will just do it will just combine concepts on top of each other.
This is starting to look pretty cool.
Yeah,
But since it doesn't say life, the universe and everything, the answer will not be 42 anyway.
But this gives, this really gives vibes of the book.
Yeah.
Yeah, there is the space. Yeah, it's actually picturing the space.
Maybe we will see ships falling from the sky.
And there seems to be some kind of a life emerging there in the middle.
It says 42 in an alien notation. It does say 42 there. It says,
yeah. Is there a large question mark?
Yeah, it seems like it could be actually. So now it's when you generate images with this autoencoder, it's not very keen on writing, but if you just use the deep dreaming, it's very keen on actually. So if you ask it for a forest, it will both make some trees and write out the text forest, which is a bit funny.
Do you know if it's sensitive to typos? So if you would write a sentence with some typos, would it still generate something meaningful?
I think it's relatively unsensitive to typos. But I guess that's from the transformer. the text encoding. It's
transformers with byte pair encoding usually manage that pretty well in other settings. I mean,
do you want to try out some other prompt here?
I have a question.
Yes.
You said that you are freezing the decoder and encoder parts, but what if you don't freeze, or you train a bit, a layer in between or at the end? I don't know. Like, would you be able to even guide it further?
So I assume you're talking about the clip encoder.
Yeah, or the connection between the two, because you have one clip encoder and then you have an image decoder. So the connection between these two at the moment, as I'm not sure if I understood correctly, but you are not training anything. You're just giving the output of one to the input of the other. And
so yes, I'm actually training the autoencoder. No, the image generative network. So the network is trained, and I think that produces a bit of higher quality images.
Okay, so you use a style GAN, but you kind of fine tune it.
Yeah, I fine tuned the style GAN a bit.
Mm-hmm. Thank you.
So I would summarize this as you can almost produce any picture that you can think of with some caveats.
What would it produce if you input the world if we don't stop climate change?
Yeah, it would probably produce a green picture. So let's try it.
Or maybe it's a climate change denier, and will show us a sunny world.
You should compare that to generating the image of us stopping the climate change.
Yeah.
So yeah, maybe it can guide us what we should do.
So at least it seems that the live demo gods are with us today. So that's good.
It's very fascinating.
So yeah, I guess this will produce something.
You almost see skyscrapers there.
Yeah. So the style GAN produces results very fast. With this, you have to have a little bit of more patience before they kind of.
My interpretation of this is New York being flooded and a lot of pollution.
Yes, I think I'm with you on that one. But here you can see that so the prior from the generative network and clip doesn't. It's okay for both the networks that you have houses in the sky, right? So
like a true dream.
Yeah. So if you would want to have like photorealistic images, you would have to add additional constraints or train a discriminator to say this is not a true picture or whatever.
Could you elaborate on that? Because you haven't. I follow you in Twitter, and I haven't seen. And I mean, you haven't aimed at photorealism yet. Is that so, or?
Yeah, it's just harder, I think. So what do you want me to elaborate on more?
Would that be a next step? I mean, how hard is it? What's stopping you?
No, me personally, I think it's just time and resources. I mean, I would love to do it, but it's a bit unclear why. More than the love of exploring at this point. But I mean, I can definitely see startups or services or networks where you want to generate interesting images. That's I guess what they aim for with the DALL-E, right? So if you can have 3 stock photos for any textual prompt, that's great, right? But there are definitely, since I'm only making images from clip, there are, of course, limitations in what that network have seen and what kind of interpolations it can do. Yeah, so we're getting short on time here, I guess. Any other questions, or then we can do? So yeah, with regards to climate change, it seems like it's going to be water everywhere. We can do a final image of God, I guess, here.
I think it was an interesting one in the chat.
Oh, I mean, okay, let's try that. I think it might go well. You can be specific if you want it to be a photo or if you want it to be a drawing or whatever.
Can I ask one more question?
Yes, ask away.
So it's right now you are going from text to images. What if you want to go from images to text? Would it be much more difficult?
I don't know. I have the intuition that it's probably something that you can do. It could probably take a GPT-2 network and kind of modify it to take in a latent vector from clip, and then but then you have to have the text image dataset, or at least a text dataset. So I think you could do it, but I'm not sure about the details or how good.
Mm-hmm.
So if I could just add something there, typically generating text is harder because text needs to be discretized. So that really depends on how well you can condition the text generation based on how well you can transfer the gradients through this discretization step. So typically you might sample from the distributions of the text generation, but that will be non-differentiable. So you can no longer go back the whole way through the text generator. So that's a typical issue with using, for example, GANs for generating text. Now there have been experiments done there, but it's much more difficult than generating images.
Thank you.
I agree with what Eric said.
This fist fight is amazing, and at some of the iterations, you could almost see this pow coming in the middle.
Yeah. You can probably spend a lot of time in refining the. I'm working with the prompt engineering to get it to become even better. But
I think Batman is winning.
Yeah. I've seen examples where people add qualifiers, so they add like high definition, not blurry photo. The picture actually gets better, which is really stupid. But, yeah. Yeah, this is fun. But I think with regards to the science, I think you would want to kind of explain why you have to regularize and what kind of regularization is interesting. And then I keep saying priors, right? So StyleGAN has a image prior for faces. How can you have a general image prior where you're not allowed to have skyscrapers in the sky? I think that's interesting, because if you could have a discriminator that can kind of have this general image prior, then you could actually just combine it with clip and go towards the DALL-E level of quality of images, but as of now, it's not.
Would it be possible to try to sample in an efficient way in the latent space of a generative model? Like if we know that there's some region in the latent space which corresponds to images of faces and others that are corresponding to something else? Could we guide this in that way, if you understand what I mean? Maybe it was a bit unclear.
I guess that I'm guessing that you would basically want a big data set of natural images, and you would want to kind of generate these fake images and do a classical discriminator thing. That's my best guess. And then you would basically exclude the weird stuff from the latent space. So God was male.
God was male.
Yeah,
and he looks like a human, but he has this nice halo, you know. Also,
he's also white.
Yeah,
man was created from the image of God, wasn't he?
Yeah, exactly. So it all makes sense.
Yeah, it all makes sense.
He's younger than I expected.
Yeah, but I don't think I have the code ready. But now that we have fine-tuned the style GAN here, we can probably sample female gods as well, actually. So if we would stop training and just
that's actually interesting. And what and sort of in what cultures and in what religions are there more female goddesses? Like it sounds like it could be more Greek goddesses then.
Yeah, let's see if we can actually do that. So here we have it. Here we have it. So we can just draw from the. So we have an infinite amount of weird gods here. We can even. Yeah, it's a bit of a double chin and beard and
a little bit of beard.
Yeah. Attributes at the same time. So I guess that's it for me.
Thank you, Ariel.
Yeah. If you have any questions or anything, I guess just reach out. Or...
Do we have some final questions?
Maybe this was answered before, but did you have a GitHub or a repo somewhere where all of this is published, or?
I don't have a public repository, but I'm working towards sharing it. I mean, in a month or so. But you can have it.
No, but I mean, I was thinking of the public aspect. So great.
Okay. Yeah.
So thank you for this captivating presentation and demo. I think it was super cool. Next week we'll have Raj Kumar Saini from Luleå University. And he will talk about working with EEG data. So that will be something else, I presume. Thank you for today, everyone. See you next week.
Thank you.
See you.
And especially Ariel.
See you.
Thank you.
Thank you.
Bye-bye.
Bye.